At the end of the last video, we calculated an average value of energy in the Boltzmann distribution, and we found that it gave us the correct answer. Now we're going to explore that and see if there are any other values that we can calculate in this statistical method. So take a look at some average values. Now remember that the Boltzmann probability distribution is essentially exponential in the energy. It has a normalization factor that we call the partition function. And this is a probability to be in the microstate K. So we can calculate the average value of any quantity in this statistical equilibrium distribution if we know what value that quantity takes in the state A, in the state K, then we can calculate its expectation value or average value by just the regular rules of statistical averages. So we're going to be doing quite a lot of these and manipulating them. One bit of notation that we introduce to make things easier to write out is to define the value beta, which is simply equal to 1 over Boltzmann's constant times temperature. So there's nothing really profound about that. It just makes it easier to write these exponents instead of having fractions. They will be equal to beta multiplied by the energy. One thing that I'll just point out here for the sake of convenience is when we have derivatives with respect to temperature, those can be related directly to derivatives with respect to beta through a change of variables or a chain rule. And those relationships look like this for any variable A. So if you don't like beta and you want to have KTs everywhere, then you can use those to change your derivatives. So the first one of these average values that we calculated was for the energy. And we did that just by plugging in the energy of the microstate K itself. The same energy that would appear in the exponential and control the probability distribution. Now we want to kind of explore if there's another way to write this. And to do that, let's put in the expression for the probability of state K. Okay, so there's the 1 over the partition function, normalization factor. And then there's the weighted sum of the energy of each state and the Boltzmann factor. Now this looks suspiciously like it could be, well, first of all, we can't do this sum exactly because, if we summed just the energies, just the exponentials, then we would get the partition function. But now we've got this EK here. We're trying to do this in general, so we don't know what the EKs necessarily are unless we pick a model. So there's no obvious way to evaluate this sum exactly for every situation. But as we'll see when we start working with these Boltzmann factors and partition functions, there's a certain magic that seems to happen with the variables and the relationships, almost like someone set this up waiting for it to be discovered, because things end up being a lot simpler than it seems like they should. So this sum here, it looks suspiciously like we could obtain this kind of term, like e times the exponential of beta e, by taking the derivative of the exponential part, right? If you take the derivative of e to the beta e with respect to beta, then you pop out this factor of ek due to a chain rule. So let's do that correctly. We will have to take the minus beta derivative of the Boltzmann factor, like that, and then that will give us minus ek from the chain rule, and then the minus out here turns it into the positive ek that we want in the sum. Our first sprinkling of magic into here is to realize that the derivative with respect to beta can be moved in or out of this sum. As long as the sum converges, this doesn't have to be done first. It can be done after the summation. So we can have this be minus 1 over z times the derivative with respect to beta of this sum, which is now just the Boltzmann factor. And what do you know? This sum is, in fact, just the partition function itself. Right? That's just z. So this average energy can be written as minus 1 over z times the derivative of z with respect to beta. But that's equal to the average energy. And that's kind of our first amazing result here. This function z that we call the partition function, initially it was just, we've got to normalize these probabilities, so we better add this up and divide by it. But now we come down here and we're saying, hey, it looks like if we just knew the function z, we could have found out the average energy from its derivative. So we're seeing that this partition function z is much more crucial to the progress of this statistical mechanics than we might have thought just by having it be a constant to normalize probabilities. So let's save that identity up here at the top. Average energy is equal to minus 1 over z times the derivative of z with respect to that beta variable that was related to temperature. Notice that we could also write this as, when we have the derivative of something divided by itself, that's called the logarithmic derivative. It's equivalent to writing the derivative of the natural log of that quantity, because the chain rule there would just give us 1 over z times the derivative of z. So we'll keep those two in mind. We'll use them in a bit. Let's look at another quantity here. We know that if we have the energy per particle and the temperature of the system varies, then that energy can go up or down, and that's related to the heat capacity of the system, right? The heat capacity here it would be at constant volume, because we're not changing the energies of the microstates, so we're keeping all the parameters the same. So dE dt would be the specific heat at constant volume. Basically, this is the specific heat per particle, because we're just talking about one particle, one entity with its microstates here. So remember those relationships I had on the first board for the derivatives. The derivative with respect to t could be equal to negative Boltzmann's constant beta squared times the derivative with respect to beta of the same thing. So that's what we would get for the specific heat per particle. And amazingly, again, we have the derivative with respect to beta of the energy. And since the energy is directly related to this partition function up here, we can just plug that right on in. It will cancel off this minus sign. And the derivatives can be combined into a second derivative. So we see that this partition function, if we take its second derivative with respect to that beta temperature parameter, that's related directly to the specific heat per particle of that statistical system. Now there's a very interesting alternative way to get this specific heat. If I take the this, let's see. If instead of plugging, so instead of plugging in for the average energy, the partition function expression, if I instead go in the direction of using the probabilities, and put in this average energy in terms of the probabilities pk and the energies ek, what I can do with this is take the derivative of this sum. So keep the sum outside and then take the derivative of what's inside with respect to beta. So we'll write this probability, oh, that's not the problem, no, so it would be EK, PK for the average energy, and then we would have the Boltzmann factor divided by Z for that probability. So we can do this derivative explicitly on this part. So we'll have an EK out front. And then we've got a product rule here, two functions that both depend on beta. So for the first one, we'll get a minus EK times the exponential divided by Z. So that's the derivative of the top. And then for the bottom, we'll have a minus 1 over Z squared. There's an EK still in the numerator from there. And then the Boltzmann factor. And then we have a dz d beta. Okay? All right, so in this method of simplifying things, I've got a bunch of minuses here. So I've got minus, minus, and minus, so I can make everything plus kb Boltzmann's constant times beta squared. And then let's take a look at what's inside this sum. So here we, because of the derivative of exponential is itself, so again we get the Boltzmann factor over z, so that turns into the probability. So here we'll have ek squared times the probability, pk. Then we've got a plus, because we killed the minus signs from this one in the front. And then we have ek times the probability. So this ek is there. The probability pk is from the Boltzmann factor over one of the z's. And then so we've got one more z in the denominator and then this derivative. But this derivative divided by z is just right there. It's the opposite of the average energy. So we have minus average energy here in our sum. And if we look at what this is actually telling us to do, we are summing over ek squared times the probability. So this first term is going to give us the average value of e squared. In the second term, the minus e is a constant, so that can go outside the sum. And the sum just then acts on these two, which gives us the average energy. So we have minus the average energy, one factor from here, and a second factor from this one. So we have minus the average energy squared. Now you know that if there's any sort of distribution to these energies, the average of the square of a quantity is not equal to the average of the quantity squared. It's in fact equal to the standard deviation of that energy distribution. So we can rename this essentially using the same notation as we would use in a statistics course, if there's this distribution of energies, then sigma would be the standard deviation of that distribution. And so we get a really quite beautiful relationship here that the specific heat at constant volume per particle is related to the standard deviation, or the spread of energy levels when the system is in a thermal equilibrium distribution. Okay. So this method becomes, very useful if you're doing a simulation of a statistical system, and you kind of set things up in a random state and let them evolve randomly, and then they shimmy themselves into somewhat of an equilibrium state, and then you can measure the distributions of energy in there and find its standard deviation to get a measure of the heat capacity. Okay, so we'll leave these two up here as well. CV could be equal to KB beta squared times the second derivative of Z or also equal to KB beta squared times the standard deviation of the energy distribution. All right, the next quantity we're going to try to tackle is one that's very important for linking up to thermodynamics, and that is entropy. So how can we inject some understanding of entropy into this statistical system? Well, remember that entropy is related to flows of heat, and flows of heat cause a change in the internal energy. So we'll consider a change in the total energy. Remember, if we have no work done on a thermodynamic system, then energy and entropy are related by this fundamental identity. Now we're just dealing with one particle, so it's not internal energy yet, but we can still relate this to the energy per particle. If we consider only changes in energy due to heat flows or due to temperature changes, then we could say that the average energy of a particle wouldn't change due to any work. Work would be a change of the energy of the microstate, EK values. The energy is not here changing due to any work, it's just changing due to the temperature or the beta value of the distribution changing. So we would write our analogy to this fundamental thermodynamic identity as changes in the average energy of a particle are related to the temperature. This is just the temperature. There's no magic here. This is just the temperature times the change in the entropy per particle. So the lowercase s there is entropy per particle. All right, so this kind of sets me up with an equation that at least puts entropy into the mix. Here, the derivative of particle entropy with respect to beta is equal to Boltzmann's constant times beta times the derivative of the energy with respect to beta. Okay. Now that's all well and good. You could actually take this energy value here and take its derivative, multiply by beta, and then sort of integrate it in a numerical sense, and that would give you a picture of the entropy. But let's try to be a little bit more symbolic than that. I'd like to be able to integrate this as a differential equation to solve for the entropy alone. But I can't do that right now because this side is not a pure derivative, right? It's got a derivative here, but it's multiplied by beta. Now, one way I can get around that is by using the integration by parts. And I'll write that in this way. So first, we've got, okay, so first I'm going to take this KB to the other side. Get that out of there. And then we're going to put in the expression for entropy, for energy in terms of the partition function. So 1 over KB times ds dB. This will be minus beta second derivative of log z over with respect to beta. Okay, so now for the integration by parts. This expression could be obtained by taking the opposite of the derivative with respect to beta of beta times d log z d beta. If we did this chain rule, we would have first a term that was beta times the second derivative of log z. That's what we've got here. But then the second part of the chain rule would just be the derivative hitting this beta and turning into 1 and having it multiplied by that. So to get this correct, we have to add on a d log z d beta. So this is like integration by parts, basically. This is your uv, your total derivative of this, gives you these two terms from the product rule, and that sets it up as a total derivative on the right side. So you can check, you just work this out and it will be equal to this over here. So the point of doing it this way is that now every term here has a derivative with respect to beta as its first thing. So we can say that the particle entropy per particle divided by Boltzmann's constant is just the, we just integrate both sides. So we'll get minus beta d log z d beta plus log z. All right, so that's an expression for entropy in terms of the partition function itself. And that's also kind of neat because then you just have to take this partition function and pop it in there. You can get your formula for the entropy of that statistical system. So we'll put that up here. S per particle is minus kb beta d log z d beta plus kb log z. All right, so this formula actually gives you a little bit of a tingly feeling in your toes, because when we originally defined entropy, we said it was equal to k times the log of the multiplicity. And now we've again got this k times the log of something. So we should be starting to get a feeling like, oh, this partition function is really important. It's like sort of the multiplicity partner in this Boltzmann distribution way of doing stat-mech compared to the actual multiplicity in that microcanonical ensemble. Okay, there's one more interesting formula for the entropy that I want to derive. This one doesn't give you any really intuition about why the entropy looks like this. We do have like k log of something, but then there's this other derivative term here, and what's that doing? So I'm going to write this as, I'm going to try to re-express this only in terms of probabilities. Now remember that the probabilities pk were equal to 1 over z e to the minus beta ek. And so in kind of a perverse way of rearranging this, I could say that ek is equal to minus 1 over beta times the log of pk times z, like that. Normally you wouldn't think of solving for the energies like this, but when I want to express the entropy in terms of only probabilities, this allows me to get rid of the e's. So let's go through this then. S is equal to minus k times beta. And then we got these two terms here. So there's a derivative of this logarithm. So d beta yes. Okay. So of course I need to express my logarithm in terms of the oh no. So what do I want to do here? Yeah, I'm going to express my derivative of log z here as the average energy. So there will be a beta that stays around. This will just be then average energy. And then we've got kb times the log of this z. Okay, so starting from there, the average energy is sum over k of energy k times probability of state k. I'm going to get rid of that energy. I want to write it as minus 1 over beta times the log of pk times z, like I said up here. And then there's that still that pk there from doing the average. And that kb log z term on the far right, I'm just going to leave that alone for a bit. Okay, so in this first term, the betas cancel each other. So I've got a minus out front. And then something fun happens with these logarithms, right? I've got the logarithm of a product. So I'll have one term, which is pk times the log of pk. And then I'll have a second term, which is pk times the log of z. And now log of z is just a constant regarding the sum over k. And of course, the sum of all the probabilities over k is just 1. So this part here will turn into a 1 after I do the sum. And then I'll have a minus kb log z coming from that term in the sum. And that will just cancel this plus kb log z that was at the back. So those two terms together amount to a 0, and the only thing that's left over is really this first one. So the minus Boltzmann constant times the sum over all microstates of the probability times the log of the probability. So this is another formula here for the entropy. Minus kb times the sum over all states of the quantity probability times log of probability. Right, so that's really also another beautiful formula here. It really emphasizes that the entropy only depends really on how the probabilities are distributed. It doesn't depend explicitly on the energy or the temperature at all. Really, it just depends on how randomized things are, right? If the probabilities are spread out over a lot of states, if there's a lot of probabilities that are very low, remember every probability is less than 1. So these logarithms are all negative values, and that kills this negative here. So if there's a lot of states that have all really low probability, then this sum is going to be big, and it's going to give you a big entropy. If there's a bunch of states that have 0 probability and one state that has only 1 probability, this sum will give you a 0, right? Because you've got zeros for all the states here, and a 1 for just one of the states, which will give you a 1 times log of 1, which is, again, a 0. So you have no entropy if you know exactly what the probability distribution, or if it has, you get a 0 entropy if it's got 100% probability to be in one microstate, and a larger probability if it's spread out. A fun way to interpret this is minus kb times the average value of log p. Right? That fits, right? It's the expectation value of the logarithm of the probabilities themselves. So that's what we can say about the entropy.